interior also the money?
No.
It's not what we can discuss.
Not so much.
Volevi dare qualche retta a quel ragazzo?
È riuscito a farlo.
Ah, ok.
Ah, the video cable?
Usually it's
Yes.
ah, here it is. A bit hidden.
Aspettiamo che arrivi.
Sì, sì.
Yes, it was. We have, I don't know, we have a lot of questions about exactly with the comments, but I think we're going to help us with that.
Non vedere come fa a vedere per seguinte, vocês como estão com respeito à instalação da máquina virtual, vocês já está tudo ok no computador de todo mundo? Tem alguém com problema de instalação? Não? Chegaram a fazer algum exercício? Brincaram um pouco em casa?
A gente colocou o modelo.
Ah, tá bom. A ideia de hoje é assim, então, praticamente, o Luciano vai continuar explicando o funcionamento do Geant4 e a gente vai fazer os exercícios, tá? Todos juntos. Eu recomendo que vocês façam perguntas, aproveitem que ele está aqui e façam perguntas, o que vocês fizerem para mim, para ele, para o Fábio, para o Matheus, para problema de instalação, a gente está aqui para dar uma ajuda, tá? E aí vocês vão ter a plenária de hoje, não vai ser às 4 da tarde, porque excepcionalmente hoje tem assembleia lá naquele auditório que vocês estão fazendo a plenária, e a plenária vai ser feita nesse salão aqui no Escola de Estudos Avançados, mas depois que eles terminarem, porque a plenária ficou para 6h30, para uma porta. Aí o que a gente estava pensando, já que vocês vão ter que ficar esperando 2 horas no vazio, assim, quem quiser, fica aqui que a gente continua fazendo exercícios de Geant4, se for interessante para vocês. Quem quiser descansar, está livre também. Não vamos cobrar a presença por isso, né? Mas aproveitando aqui. Né? E qualquer dúvida, gente, por favor, chame a gente. Às vezes sentado junto a gente faz rapidinho e resolve. Hoje o professor Luciano vai começar com a primeira parte do Primary Generator, que é um pedaço do programa que define o input que você vai dar para a tua simulação. Que tipo de partícula que você vai usar, qual a energia que você vai usar, qual é o ângulo com que você vai lançar a partícula, se vai ser pontual, se vai ser uma função. Então, praticamente e daí ele vai discorrer sobre todos os outros programas do Geant. Qualquer dúvida, se vocês não entenderem alguma coisa, por favor, aproveitem e perguntar. Eu tenho certeza que no final da semana, sexta-feira, vai estar todo mundo já fazendo os seus programinhas. Tá bom? E a ideia é que vocês espalhem esse conhecimento para os próximos que vierem. Alguém tem alguma dúvida ou quer falar alguma coisa? Não? De repente, se quiserem sentar aqui mais para frente, por causa da tomada, né? Tá. Então, você não tem problema de instalação também, né? Não, já. Já está bem instalado. We can start. Okay. They agree to stay here for more two.
Okay, that's up to them. I will be here, so if the lecture will be over, but I will stay here if you want to try. I understand that yesterday we had some problem with USB controller and keyboard, which was Portuguese or not, so maybe you couldn't really go into the exercises which were supposed to be done yesterday. So if you want to take this extra time to fill the gap, I will be here around. That's your choice in any case. So if you want to take this opportunity,
nobody has problem with the installation.
Okay, good.
Everybody's okay. Now we need to start to play.
We took a while to have everything working, but it seems that at the end of the day we did that. So the lecture today, as anticipated yesterday, I'm going to cover the mandatory parts of a Geant4 program. So today it will be the geometry, so how to define your experimental setup, and the primary generator, so how to decide which kind of particle is chopped, which energy, which direction, and so on. Tomorrow I will say about the physics, and on Friday I will say about the retrieval of the information from the kernel, so the optional user actions that are in any case needed to get an output. Okay, so let me say something more general about units and material in Geant4. The message is that Geant4 is not providing any default unit of measurement. So when you write some input data, for instance, the length of my detector, it's always a good idea to multiply explicitly by the unit of measurements in order to have this thing clear. So if you want width, 12.5 times meter or times centimeter or times millimeter. So the good way to give the unit of measurement is always give them explicitly, like a multiplication. And this works pretty much the same for the other units like density. So 2.7 times gram per centimeter cube. So, and there are a number of units that are already defined in Geant4, and in principle you can define new ones if you want. So everything is contained in this file, which is G4 system of units.hh. So if in your program you have include of G4 system of units, you will have access to all the units that are defined in Geant4. So when you want to input data, you just multiply. When you want to output the data, you have to divide. So for instance, if you want to get an energy in output in, I don't know, in MeV, you just divide it by MeV. So it is not really fully true that Geant4 has no default units. Actually, for energy, it's MeV, but it's always good to have a transparent treating of the units, so that you really always know which units you are talking about. So if Geant4 changes from one day to another, the default units, your code will always work as good as before. So you are really not depending on what's the choice of Geant4 for the definition of the units. So this system of units in Geant4, it has quite a lot of units: millimeter, nanoseconds, energy, charge, temperature, mole, and so on. So there are a set of basic units, and you compute all the others starting from the basic one. So this is the typical way to write on the screen a number with its unit of measurement. I don't know if you know this cout and handle syntax, which is the C++ way to write on the screen. So this means write on the screen energy divided MeV, and this is a string which is displayed on the screen, and then end the line. So go to a new line. So if in some cases you just don't know what's the value of what's the anticipated value of the variable that you want to get, so you can use these G4 best units and say that it is a length. So the value will be printed in kilometer, meters, millimeter, or whatever, depending on its value. So if you don't know if a number is 10 to the minus 14 or 10 to the 15, so you just don't know which is the best units, which is appropriate, whether MeV or electron volt or TeV, you just can use these G4 best units, which is giving the best unit according to the value. And you can also define custom units by combining basic units that are defined by Geant4. So this was about the units of measurement. The first step to define a geometry, you can think about two steps. First, define the materials, and then define the volumes which are made out of those materials. So you can have different levels of definition of materials. The most basic is the isotope. Then many isotopes, they build up an element. Then many elements build up a material. And in principle, you can have compounds which are made by mixtures that are made by many materials, and it is again a material. And you can associate some attributes to each material, like the temperature, the pressure, the state, whether it is a gas or a liquid or a solid, and the density, of course. So as the name they say, the isotope and the element, they describe the property of the atoms. So like atomic number, number of protons, number of neutrons, atomic mass, binding energy of the shells, and so on. While the G4 material is what is used by Geant4 actually for the calculation, and it describes the interaction property of the matter, like pressure, energy, pressure, state, density, radiation length. So the element information is just used to calculate the material information. So what is used at the end of the day is the G4 material. This is what Geant4 uses to define the property of a material, which can be quite a lot of information because it includes density, which is mandatory, but it can be the state, the temperature, the radiation length, and so on. And those information are calculated starting from the elements. So this is the basic way to define an isotope. So the parameters that they get are a name, which is a string that you choose. Then the other information that you have to feed is the atomic number, the total number of nucleons, and the atomic mass. So, and then you can combine combine many isotopes to make an element. So for instance, you can, from an element, you can say, okay, you add this isotope with this abundance. So you first define the isotopes, and then you attach the isotopes, each one with its own abundance. In most cases, you don't need to do that, because the Geant4 default is the natural isotopic abundance of the elements. You need to do this job of building an element from the isotopes only when you have enriched material or something which is not the natural composition of the element. So in most cases, you don't have to go through the definition of an element from the isotopes. So in general, you have, as I said, what Geant4 cares about is the G4 material. And you have basically two ways to define a material. So if it's an easy case, suppose that it's a material which is made only by one element, like aluminum or lead. So this is a material which is not a chemical compound, it's just made by one element. You can use this short syntax in which you define the material, a pointer to G4 material, and the parameters that you pass are a name, which is your choice. It's any arbitrary string that you choose, the Z, the A, so the molar mass, and the density. So this is a way to build a material which has only one element, like lead, iron, argon, liquid argon. So this is an easy way to do that in the special case that your material is composed by only one element. This is of course not the general case, because in other cases your material is not a mono-element material, but maybe it's a chemical compound. Suppose that you want to define water. So water, you need oxygen and hydrogen to build water. So first of all, you define the elements. So I define the element hydrogen, which has Z1 and atomic mass 1.01 gram per mole. And don't forget to put this gram per mole, otherwise you get something which is completely different from what is meant. Then you define the oxygen. So again, the Z is equal to 8, the molar mass is 16 gram per mole. And then you use oxygen and hydrogen to build up a material, which is water. So you define a new material, which is called water, which has the proper density, and which has two components. So that you say, okay, you add the first element, which is hydrogen, 2 atoms, and then you add another element, which is oxygen, which has 1 atom. So this is a way of building a material starting from the chemical formula. So you first build the elements, and then you just combine the elements to make the material. And you have two ways of giving the composition. First, if you know the chemical formula, like in the case of the water, you give the number of atoms, like H2O. You give the 2 and the 1 here. In some other cases, you can give not the stoichiometric numbers, but the fraction in mass. So you say that oxygen is giving the, 80% of the mass, and hydrogen is giving the 20%. I just say two numbers. So you have two ways of defining materials in this case, either by giving the chemical formula, or by giving the mass fraction instead of the number of atoms.
Sorry,
please.
The previous one, do you need to introduce the density of water or the
Yes.
for calculate?
No, the density it's something that you have to feed.
For the water.
For whichever material. Density, they are not known. So
Okay.
if you take also water vapor, it's water, but the density is not one.
Okay.
So that's the element information is just the composition, while the density you have to feed in any case. So you can also make compounds material which are mixture of materials. For instance, you can do something which is, an aerogel, which is made by carbon, so an element, then quartz, which is a material, and then water, which is another material. So you can do complex mixtures in which you have elements and materials all together. So for instance, you define this new material which is called aerogel, So you define the density, and you say that it has 3 components. So first of all, you add the quartz, which is another material. So you are making a material building out of another material, which is a fraction of it. So you give the fraction of mass. We suppose that it is 62.5%. So you are making the aerogel, which is made out of 62% of quartz. Then you add 37% of water, which is another material. And then you add a carbon, let's say 0.1% of carbon. So add material, add element. And you are building a material altogether, which is made of other materials and elements. This is the other syntax. Instead of giving the numbers of atoms, you give the fraction of mass. And Geant4 will take care of making the calculations and to derive the average properties like radiation length, so material properties that are then used for the tracking of the particles. So Geant4 will use this material information to calculate the cross-section for the particles to be tracked and so on. So all the information about its interaction of particles with matter. So all the information about the matter, so the target, it's calculated according to this G4 material. So in some cases, like at the case of a gas, you want also to specify, for instance, temperature and pressure, because this can be affecting physics, like the stopping power calculation of the thermal scattering. So you can give the temperature and the pressure and use this information as additional optional arguments to the material definition. So in this case, we are defining carbon dioxide, so CO2, at 325 Kelvin and 50 atmosphere, and with a given density. So in principle, you can stay here. So all these 3 arguments are optional, but in this case, we are saying that it is a gas. We are feeding the temperature and the pressure, and then we build the carbon dioxide by 1 atom of carbon and 2 atoms of oxygens. Another warning is that Geant4 does not handle vacuum. So when you want, really, as I was saying, you need to have a big volume around, which is the Born volume. And in some cases, it's made maybe of air. In some cases, it should be vacuum or something like that. But Geant4 is not able to handle vacuum. So vacuum for Geant4 is a material with very, very low density. So you can define vacuum as something which has, I don't know, 10 to the minus 25 gram per centimeter square. So if you want to define something in which particles do not interact, you need to define a gas with very low density. Geant4 offers some additional help for this. Of course, the 92 elements, it's stupid that, well, they are 92 and then that's easy. So you don't have, it's stupid that you have every time to define oxygen from scratch, since it's out of one of the 92. So Geant4 includes a NIST database, a database from the NIST American entity, in which all the information about elements are already included. So atomic number, Z, isotopic composition, and so on. So in this case, you don't need to define oxygen or hydrogen by hands, but you can just use the information which is provided from this NIST database. And you have a few commands.
Teacher,
Sorry.
if I want to use that database, I have to type this link in a program?
No, that's really the documentation, the page of the documentation of the NIST. Then I'm going to show you how to use this in the real life. That's just for your information if you want to see what this database contains. It's not really to be written in the code. So the NIST contains the information of all elements from hydrogen to californium, and then it contains a number of compounds that are of common use, like liquid argon, lead tungstate. So in some cases, the material that you want to define, it's already there from NIST. So you can have, for instance, air, which is already defined. So you can use the NIST definition instead of writing your version of the air. So in this case, it's a bit easier to define materials, and you can also use a combination of NIST materials. So for instance, if you want to use the water definition, which is from the NIST, you just get the NIST manager and, okay, you ask the NIST manager, okay, find me the material which is called G4_water, and that's it. So you instead of using your own definition of the water, you take the one which is already provided within Geant4. And if you go to the Geant4 webpage, you will find the list of all the materials that are available. And water, air, all of them are all, let's say, the mostly common, the commonly used materials are already available. So this is a part, you will see better when you take the exercise about that, because I will really ask you to build a material out of elements in the task 1 exercise. So this will be a part of the exercise today. So basically you have two ways to define materials. One is that you code yourself, so you feed either the chemical formula or the mass composition. If the material that you need is already in the NIST database, you can just use the one which is in the NIST database. So now I'm moving to the second part, which is, okay, you build the materials. So suppose that you have a volume which is aluminum, a volume which is sodium iodide, and a volume which is water. You define the materials to be used, and now you have to define these volumes, which means the shape, the dimensions, the placement, the rotation, so all the information that are required in order to have this real volume placed in your geometry. So as I was saying, you have to provide a description of your detector, and the description is made out of volume, and all of them are contained in a big box, which is the word volume. As I was mentioning yesterday, the word volume must contain everything, and the function, which is from the base class, which is the construct function that you have to write. The job of this construct is to return the word volume with everything inside. So this is the way Geant4 takes a geometry, is through this construct function of the geometry base class. So what you have to do in this function is to define all the shapes that you need. Some volumes will be boxes, some volumes will be cylinders, some volume will be spheres, something will be more complicated. You have to build all the materials that you need. You have to place the volumes in the space. So you have a cylinder made out of water, but maybe you want in a given position, or you want it to be rotated with respect to the reference frame or to the other volumes. So you have to construct and place all the volumes. And optionally, you can do these 3 actions. So you can say that some of the volumes are interesting for you in the sense that they are sensitive. You want to know what happens inside those volumes. You can associate magnetic fields to them, so to magnetize a part of the geometry. Or to define visualization attributes. For instance, you want to see one volume in blue, and you want that another volume is drawn in red, and so on. This is done in this class, which I mentioned yesterday, which is the base class G4V user detector construction. As already said, again, the G4V means that it is a base virtual class, so that you must implement it in order to have a working simulation. So in order to build each of those, there are in principle 3 layers, 3 logical layers. First of all, you have to define a solid. So what's the dimension and what's the shape of the volume that you want? Let's say I want a box of 1 meter times 1 meter times 1 meter. That's a piece of information. It's a solid, the G4 solid. Then you add something more. You want a box which is made of water. So you are adding some more information, which is material, sensitivity, magnetic field, and also hierarchy. So you can include volumes one inside the other in a hierarchical structure. So this is the second step, which is called logical volume. So it's the shape plus something more, which is the material, the sensitivity, the magnetic field, so some more properties. And the third layer, which is the final one, is that you take the logical volume and you place it into the coordinate system. So it's a logical volume placed somewhere in this coordinate system or rotated. So you may have a volume which is placed here, a volume which is placed here but rotated. So this is the final part. It's the physical volume. So again, the basic strategy is quite simple. So first of all, you create the solid. So again, you have to specify the shape and the dimensions. So for instance, in this case, we are creating a box, so as a parallelepiped. You assign a name, whichever name you like, and then the dimensions, 1 meter, 2 meter, 3 meters. So these are the three sides of the solid. So you made it as a solid. Now you add some more information. So you say that you want a logical volume, which has the box as a solid, and then with some material attached to it, and then this is a name. So the second step is taking the first and adding the material information. And then you have the third step, which is taking the logical volume and putting it in certain coordinates, which is the position, x, y, z. So this is the coordinates where you put this volume, and the rotation with respect to the reference frame. So the general reference frame that you have is done this way, so it's placed in the center of the world volume. So everything in Geant4 is referred to the center of the world volume. So this is setting the system of coordinates. So all translations and rotations, they are referred to this reference frame. So this is the three steps. First the geometry, the box and the dimensions. Then you add some information, which is the material, and then you place this logical volume somewhere in your world. So it means with certain coordinates and with a certain rotation. In principle, the same logical volume can be placed many times. Suppose that you have a modular detector in which you have the same volume replaced many times. So in this case, you have only one logical volume which you place many times at different coordinates. So this is helping quite a lot if you have modular geometries in which you have some shapes that are repeated many times. Take a calorimeter in which you have many sampling slices, liquid argon lead, and then all together, it's also always the same. It's a repetition of a basic module. So you just create one module and then you place it many times at different coordinates. So there are quite a lot of shapes that can be defined in Geant4. There are the basic shapes: a box, a tube, which means a cylinder, a cone, a trapezoid. And you can do something more complicated like polycone, polyhedra, twisted tubes, or you can do something which is defined by the boundary surfaces. So you can build quite complex surface. And the most flexible way is to do Boolean solids. So you want to do something which you can combine solids by adding, union, subtraction, or intersection. So what you can do is that if you want to, I don't know, you need to do a strange shape which is, I don't know, cylinder, and then subtracted a cone. So something which is done like that. In this case, you can build it as a subtraction. You take the full cylinder, you take the cone, and you subtract the cone from the cylinder. So you can do some operations with the volumes so that you can build complex shapes that you need. So this has to be done with some care because the simulation is getting a bit slower if you use many of those things. But if your geometry is made out of complex shapes, you can do by using Boolean operation between solids. This is, for instance, a way to define a tube, which is a cylinder or a shell of a cylinder. So you have to give the name, which is an arbitrary string. You have to give the inner radius. You have to give the outer radius. You have to give the z, so the height of the cylinder. And you have to give the angle. So in this way, you can build a full cylinder. You can build an empty, a no-load cylinder. And you can build just an arc of the cylinder. So you can, according to the parameter that you give, you can get quite a lot of different shapes. And basically the same for the cone. If you have a look at this section of the material, of the manual, you will see that there are quite a lot of shapes that can be built with Geant4. And this is what I was mentioning. You can combine solids by Boolean operations, so units, union, subtraction, and intersection. So altogether, subtraction and intersection. So this operation required that you have two solids and one operation between them, and optionally a transformation of the second with respect to the first. So the result, please.
If I want to, for instance, like you said, to build in a box a lot of repetition of the same volume, do I need to repeat that block of logical, physical,
Well,
times?
No, not really. When you do it, what you do is that you create only one logical and you place it many times. So the logical volume is only one. And you have many copies of the logical volume placed at different coordinates.
Then in the physical part, do I need to repeat it?
Yeah, you can do in a loop, maybe.
Yes.
So you don't need to have many copies of the logical volume. It's only one logical volume which you place many times in different coordinates.
So I define the solid, the logical volume, and then I do a loop in the...
Yes, exactly.
And how do I recognize that the particle is in this volume?
Oh, those volumes, they get a copy number. So the volumes, you can either call them differently, or there is a copy number. So each of the repetitions has a different number, 0, 1, 2. So you can use this copy number to define in which of the copies you are living. So you have a box here, then you have a logical volume which is repeated many times. It just plays many times, and this is copy 0, copy 1, copy 2, copy 3, and this is used to distinguish in which copy you are living.
Sorry, please.
Please.
These copies you need to give the coordinates
Yes.
of each copy.
Yes.
And the coordinate that I give is the center of the geometrical
Yes.
object.
Yes.
And what happens, for example, if I have this, the figure that you draw in there, the cylinder minus the cone.
You are right.
How do I place that?
Okay, so by convention, the center of a Boolean is the center of the first solid which you give.
Okay.
So you are doing this minus this, basically. So the center is this one.
Okay.
So the Boolean solid, it gets the center of the first solid which you define.
Okay.
This is just a convention. And another piece of information that you can use this solid to have another Boolean operation. So you can do a Boolean of a Boolean. So you can take this thing and then subtract a corner here. So you can use a Boolean as a starting point for another operation. As I said, this should be treated with some care, because again the cost of navigating through the complex shapes is of course increased. So if you have many of those Booleans, your simulation gets slower, because actually in order to know in which points you are, the calculation is getting more complicated. So at some point there is a trade-off. You have a strange shape. Do you really have to implement it as a strange shape to gain something by adding this small corner, or I can just forget it? And so it's again a trade-off. If you have a more precise simulation, it's lower, which is if you want something which is more precise, you have to pay the price, which is more CPU time. But do you really need to be so precise? So this is where the physicists come in. So you have to decide what's the precision that you want. So you want to do a good job, but not overdo. So you don't need to be too much precise if you don't need it. And still, that's where the physicist comes in. To write a code, a computer engineer is much better than a physicist. That's sure. So the physicist comes to just to define this optimization thing. So you have to define the precision if you want to be precise but not over precise, to assess if the results make sense. So suppose that you have a simulation and you get results. You are the physicist and you should check if the results, they make sense at least. So if it's something which is reasonable or not reasonable. This is still a part of the job of a physicist. Not get blindly the results that you get from any simulation. The second step is the logical volume, which is containing basically all the information about except the position. So you take the shape and the dimension from the solid, and then you now add something more. You add the material, which is mandatory. Optionally, you can add the sensitivity, some visualization attributes, and possibly the other volumes. So you can organize the volumes within a hierarchical structure. So you have the word volume, then you have some volume, which is maybe aluminum, and here you have another volume which is inside this aluminum, which is completely inside, and you define it to be the daughter of the aluminum. So you say that one is inside the other. So you're just defining kind of hierarchical structure. So this is also part of information which is going into the logical volume. So this is the way to define a logical volume. You have to feed the solid, so either the box, the tube, the cone, whichever solid that you define. You have to feed the material. You have to feed a name, which is an arbitrary string. And those other arguments, they are optional. So if you want to define a magnetic field or a sensitivity property, you can do or not, depending on your case. So when you place a volume into its mother volume, the translation and the rotation is done with respect to the coordinate system of the mother. Let me try to make it more clear. So you have the big world volume here, which is global reference frame. Then you place here a first volume, which you called people. Any name that you like. So the coordinates of the center should be placed with respect to the mother reference frame. So this is, okay, you want to place this, and you give the coordinates. Then you want to define another volume, which is inside people, and which has another name, it's the daughter. So in this case, the coordinates should be referred to the mother. So daughters refer to the coordinate system of the mother. At the end of the day, everything is referred to the word, but when you place a volume inside another, it should be referred to the coordinate system of the mother. And the rotation the same way. Quite obviously, if you are having a daughter of a volume, you cannot have it this way. So you cannot get out from the volume. So you cannot, it must be completely inside the mother volume. Otherwise you get an error.
I'm sorry, how do you give a rotation with what kind of angles?
You can define by rotation matrix, so Euler angles.
Ah, okay.
So, or you can build, yeah, there are some simplification, but basically you can give a rotation through a 3D rotation matrix with the three Euler angles.
But you have to multiply your geometric form for a rotation matrix.
You have to multiply what? No, this will be done by Geant4. So you just give the rotation matrix and the shape, and Geant4 will take care of applying the transformation.
Ah, okay.
So you just give the matrix and the volume. So you just say, okay, I want a cylinder here, and I want to be placed like that. So you feed this, you feed the rotation matrix, and Geant4 will do this for you.
Ah, okay. Perfect.
So that's the recipe. On the other hand, if you have two volumes that are daughter at the same level, they should not overlap, of course. Otherwise, if you have two volumes overlapping, in the point of the intersection, you don't know where you are. So if it's belonging to the which of the two materials. So you should avoid to have volumes that get out from the mother or volumes that overlap. This is really a mistake in a simulation. You can get in the lucky case you get an error message. In the unlucky case you get random results. So it's much better to have a clean error message or a clean crash than to have a simulation which runs and that gives you no sense results. So this might happen if you have a problem with the geometry, that you have no sense results. So this is what I was saying, is that the daughter volumes are referred to the reference system of the mother. So as I said, you can place the same logical volume many times at different coordinates. Suppose that you have a mother volume with these volumes inside, then you place the mother once more, it will contain again all these things. So if you place a mother many times, all the daughters will be placed as well. So that the entire envelope will be copied. So this is what happens if you place the same logical volume many times. So all what is inside is also repeated. On the other hand, the Volt volume must be containing everything, and this is defining the global reference system. So if you, the tracking of Geant4 is referred to this global coordinate system, which is the center of the Volt volume. The physical volume is the final level of placement of a volume. So it's a logical volume which is placed in a coordinate system and with a possible rotation. So you can do one placement at a time, or you can use some of Geant4 tools in order to have an automatic looping, like the replicas or the parameterized volumes. So the most basic tool, which is what is shown in the exercise, is the PV placement, which is a physical volume placement, in which you take a logical volume and you just place it by giving the coordinates and the rotation matrix. So there are a few variants available, but the basic is that you feed the rotation matrix, the coordinates of the center, the logical volume it belongs to, the name, and the logical volume of the mother, so that you are placing it inside some mother. Some people, they have different preferences of how to see rotations. So you can either you first have the translation and then you have the rotation of the mother frame to define a position. Some people, they like this. It's easier for me to first then the translation and then to rotate the daughter. You are getting the same thing, but it's just rotation in 3D, they not commute. So you have to take care of if you rotate the mother volume or the daughter volume. And there are two versions of the PV placement according which one of these recipes it's more fitting to your way of 3D visualization. So usually I use this thing. So I first move the volume and then I rotate the daughter. As I was mentioning, if you have volumes that get out from the mother or two volumes that overlap, that's bad. That's a mistake in a Geant4 simulation. It's not always easy to find this. As I was saying, in some cases you don't get a clean error message, but you get random results or something which does not make sense. So it is very good that the geometry is well checked and debugged. So there are some tools in Geant4 which help in debugging the geometry, like the optional check, which is done in the construction, or you have some graphic tools that helps you to find this kind of problems, either something which gets out from the mother or two volumes at the same level of the hierarchy that are overlapping.
Sorry, in the previous graph with the objects C and D, the common surface that they share, is that a problem? For example, if C is made of lead and the other is made of, I don't know, carbon?
In principle, this is not a problem, because Geant4 it has an internal tolerance. So they are not just sharing the surface, but Geant4 will take them a little bit apart. I don't know, 10 to the minus 8 centimeters. So it will add a tolerance. From the personal experience, it's always good to separate them, so that maybe you have 1 micron here in the middle, just to be sure that they are not overlapping. Strictly speaking, it's not a mistake, but this is not something that I would recommend to do. So one of those tools is done at runtime, and this is activated by putting true to this argument of the constructor of the PV placement. And this is taking some CPU time, so you want to check it once and then to deactivate it. Something, this I'm not going to say. In some cases, some experiments, they do have a magnetic field. So you want to define a magnetic field and let charged particles to be affected by the Lorentz force. So what you can do is to define the electromagnetic fields in the coordinate system. So by feeding the 3D map of the field, so you give the field according to the coordinates. This is the most general way. You give a map of magnetic fields versus coordinates. And then Geant4 uses numerical methods like Runge-Kutta to integrate numerically the differential equation and follow the motion of charged particles. So this is the way which is done in Geant4. You know that the steps in the tracking, they are supposed to be segments, while when you have a magnetic field into the plate, you split the segment into parts or in more parts, and you just approximate the curve which is done by magnetic field through 2 segments. So you increase the number of steps because you want to follow the curvature which is induced by the magnetic field. Still, in a computer, you don't have the curve, but you will have many steps performed in order to keep into account this magnetic field bending. So this is the basic way to create, for instance, uniform magnetic field. If you want to have the same in the entire volume, you just give the 3D coordinates, the 3D intensity, the vector intensity of the magnetic field, and you just instantiate it. G4 uniform field, and you give the intensity of the field. The most general case, of course, if you have a different magnetic fields versus coordinates. So in this case, you have to feed the map of magnetic intensities and 3D vector intensities versus the coordinates. This is what I had for geometry. Before going to primary generator, maybe I have a different proposal. We try some exercise with geometry. So you will, if you go to the same, let me go to the proper slide. Here. If you go to this link which I gave you yesterday, now there is the task 1 which has been uploaded. So I suggest that we take maybe 1 hour for this exercise. Maybe I will really delay to tomorrow the primary generator. So let's stay with the geometry only today. So since there is no plenary lecture at 4, as Anna said, I will be here. So since yesterday maybe you didn't go through the entire task 0, and you want to try it today to go from 0 and 1, you can take the time after 4 p.m. and before the plenary to play a little bit with these 2 tasks, and I will be around to answer questions if you have. So if you, it's really up to you. If it's the lecture will be over at 4 formally. So if you want to leave, you're free to leave. Otherwise, if you want to stay here to try some more exercises, we'll be happy to stay here.
Of course, we will break.
Sure. It's not any. I'm not planning to give any other lecture with the beamer and so. So if you do exercises, you take a coffee. It's really up to you.
I don't know how many of you finished task number 0, because I personally try to run the commands and the program makes something, but sometimes I didn't understand exactly what I was doing. So I don't know if all of you finished the task 0 because it will be fine, I don't know, to solve it on the slides, on the board, I don't know, and try to make questions about it and try to understand exactly what are the comments doing.
That's a good point.
If that proposal is good or not.
Yes, this makes sense. So maybe let's do like that, that if people, they do not finish task 0, they have some time to do now. So maybe at 3:45, maybe we discuss all together the task 0, so that if you have anything which is still puzzling to you or you didn't go through entirely, we can discuss all together. Okay.